Welcome to the lecture about conditional feature importance. We'll talk about the extrapolation issue and conditional sampling, about conditional feature importance, CFI, and the interpretation of CFI and its difference to permutation feature importance, or PFI. So remember, the idea of permutation feature importance was to replace the feature of interest xj with an independent sample from the marginal distribution, for example, by randomly permuting observations in the feature of interest. The problem was that under dependent features, the permutation leads to extrapolation. So we'll see an example soon. Now, to solve that problem in the conditional feature importance, the idea is to resample the feature of interest from the conditional distribution. So we take the conditional distribution of the feature of interest xj, conditioning on x minus j, so all other features except the feature of interest. And that preserves the joint distribution. So to look at an example, let's consider two variables, x1 and x2, where x2 is uniformly distributed and x1 has one standard normal distribution if x2 is smaller than 0.5, or it has a different normal distribution if x2 is larger than 0.5. So we can see it here on the left in the black dots. So here's this split on 0.5, and the black dots are here in this corner below that line, and they're on the full support of x1 in the upper part. And now the problem is, if you permute x1 from the marginal distribution, then you see that x1 on the whole data set as the marginal distribution is here on the complete range of x1. So this will lead also to values, the bottom here, so the blue crosses are the permuted data, even when the original distribution didn't have any data here, or the original data didn't have any data points here. So the joint distribution and the original joint distribution is 0 down here, but our by the marginal sampling, we get data points down here. And if we now do conditional sampling, for example, the very simple solution here, we introduce a split here and we do one round of permutations in each of them, then we get a good approximation here, and we also get a good approximation here. So by splitting the data, we'll get a conditional distribution. If you can do that in a little bit more systematic way, and you will find that approach in this reference. So let's talk again about that extrapolation issue. So remember from the permutation feature importance lecture that we had this data set where the target was only dependent on x3, and x1 and x2 were highly correlated, and x3 and x4 were just noise terms with all noise terms independent, and a linear model fitted with these two effects canceling each other out, and an effect of x3. We had this relationship, so highly correlated x1, x2, and we also see, as on the slide before, that x1 has values on the full range here. So if we permute x1 without looking at x2, we'll end up with a permuted data set like this, which looks completely different. So it does not preserve the joint distribution. And that leads to values of permutation feature importance of x1 and x2, which are quite high, but they should be 0 because those two effects in the prediction always cancel out. And the reason is that this permutation leads to unrealistic observations, so basically all the values which are not here on the diagonal. And because of that, x1 and x2 are considered relevant. by PFI. To solve that with the conditional feature importance, what we do is an algorithm which is quite similar to the permutation feature importance. So we start with an error, with calculating the error with the unperturbed features. Then we do that again with the perturbed features. But this time we sample from the conditional distribution and not from the marginal distribution. And we repeat the permutation, let's say m times, and average the difference of the errors. So we calculate an empirical risk, so a loss here of our model using our perturbed dataset. We do the same empirical risk calculation for our model with the original dataset. We take the difference of that and we average that over our m repetitions, and that gives us our CFI estimate of our feature set of interest S. And here d tilde S conditioning on minus S is the data set where features xs are sampled conditional on the remaining features x minus s. So that's the same algorithm as the permutation feature importance. The major difference that we sample here from the conditional distribution and not from the marginal distribution. So what does that mean? For the interpretation, it means that because of the conditional sampling to all other features, the CFI quantifies the feature's unique contribution to the model performance. So it will be the additional effect, additional to all other features. That gives us some entanglement with the data. So if the feature XS does not contribute unique information about the target, so X, S, and Y are conditionally independent on X minus S, then the CFI is 0. So that's because under the conditional independence, so if here this XS and Y are independent, conditionally independent, conditioning on X minus S, then the joint distribution after permutation is the same. And that means no prediction relevant information is destroyed by the permutation when it's conditional on the other features. So, but CFI is also entangled with the model, not only with the data. So if the model does not use a feature, then CFI will always be 0. And that is because we can basically do whatever we want with the feature. So any perturbation, it won't change anything as long as the model does not use a feature. So if it's a penalized regression, for example, and it has a 0 coefficient, or if it's a tree-based method and it's never used, then it won't change anything. So it's important that CFI is entangled with the data and with the model. So if we go back to our 3 interpretation goals, the first was that the feature of interest is causal for the prediction. And here, if the conditional feature importance is non-zero, then the model relies on that feature in some way. So that's similar to the PFI. But here again, the other direction does not hold. So it can be that the model relies on the feature, but the conditional feature importance is still 0. So the example here would be 2 highly correlated features, and they could just replace each other. But we'll see that on the next slide. The second interpretation goal was, does the variable contain prediction relevant information? So here, if xj is not independent of y, so if there is some dependence, but it's conditionally independent, conditioning on x minus j. So if xj and x minus j share information, so classic example, 2 highly correlated features, then the CFI is still 0. So that's the case where the PFI would be non-zero, but the CFI is 0. And if xj is not exploited by the model, then even if it is not involving a true target, then CFI will always be 0. So that's the entanglement with the model from the previous slide. And the last interpretation goal was, does the model require access to XJ to achieve its prediction performance? And that's exactly what CFI wants to answer. So if the CFI is non-zero, then it means that the feature contributes unique information. So unique information meaning xj being dependent of y conditioning on x minus j. But still, remember, it only uncovers the relationship that were exploited by the model. So what's not detected by the model can also be not detected by the CFI. So let's compare the PFI and the CFI on our example data we have seen several times. So again, the target only depending on x3, that highly correlated x1 and x2, and the linear model with the canceling out effect. And now if we have already seen results for PFI here, and we have seen that x1 and x2 get an effect, even though it shouldn't, because they cancel each other out all the time, so there shouldn't be any effect. And that's but we do see that effect in PFI, but we don't see that effect in CFI. So here you could say that the conditional sampling correctly assigns a zero feature importance to x1 and x2. And that's because x1 can be reconstructed from x2, approximately at least, and vice versa. So if we condition on x2, then x1 is not important. And if we condition on x1, then x2 is not important. So both are irrelevant.